C2 and C3. So then, I mean, for whatever reason, I have a 0 level that doesn't matter where nothing happens. It's not that important. And then, so the first thing I'm going to do is just sort of blister open in some way. So now I've cut open along those curves, and then I re-glue with a twist. Okay, that's the schematic for what we do. But then the point is to observe that what have we, in some way, we are removing this cutting open along an angular neighborhood of a circle really is the same thing, what's cutting open when we're going to remove something. It's the same thing as removing a solid torus neighborhood of that circle. And then closing it up again is putting a solid torus back in. Okay? So the first claim is that cutting open along, I'm going to say a neighborhood of CI inside I cross sigma and re-gluing is the same as removing. Same as means produces a manifold diffeomorphic to, as removing a neighborhood of CI inside S3. So this is a solid torus neighborhood, and replacing solid torus. Somehow replacing it with solid torus. Now are there any questions about that? I want to now try to dig into really how the solid torus is being replaced. You might think that that's enough to prove that this 3-manifold is the boundary of a 4-manifold, because, and this is not quite right yet, but the idea is going to be, so this is some kind of surgery. Remove solid torus, we glue a solid torus back in. And what we showed is that if you take, so notice that why are we starting with S3? We're starting with S3 because S3 is the boundary of the simply connected 4-manifold. Okay, S3 is the boundary of the 0 angle. And then we know that if you attach 2 handles along knots in the boundary of anything, then you change the boundary by surgeries of this kind. And if you do surgery, so you might think, well, if you do a surgery of something like this, then you've attached a handle. We have to be a little careful about exactly what kind of surgery we did. Because remember, the surgeries are very kind of special in the sense that you've got a parameterized S1 cross D2, and you replace it with a D2 cross S1. Anyway, you'll see in a moment that I want to show that this is a particular kind of surgery. So let's investigate this surgery more carefully. And in particular, what I want to do is I want to investigate where does the meridian of the new solid torus go when you do this glue. There's a beautiful picture that I'm going to try to reproduce. So I remember reading the paper by Licorice when I was a grad student and I enjoyed it. So I recommend looking at that paper. I will try to reproduce this picture from Licorice, which so we're going to sort of draw sigma as the plane board. Plane coming out. So imagine this is our surface inside our 3-manifold. And now imagine that we are our curve, this is I cross sigma. And here's our curve CI running through. Really, I've zeroed in on an angular neighborhood of I cross sigma. Okay, and then this is because actually there's a product structure happening here. Okay, so it's three-dimensional thing. And now, what I want to do is I want to, so I want to realize this process of opening up along sigma and going back down as what I'm going to do is first I'm going to dig a trench along CI in the stuff just below I cross sigma. So I'm going to dig a trench and dig a trench and then fill it back in, right? So what do I mean by digging a trench? You're going to get something like this. So I'm removing something from, I guess, I minus 1, this down here, this is sort of I minus 1 cross sigma, and this is I cross sigma here. So I'm removing something, I'm removing I minus epsilon cross an angular neighborhood of sigma, to be very precise, okay? And so but remember that it's really all glued to, originally there's also the stuff above it. We're temporarily displacing it above it, so, well, I won't try to draw what's above it, but you know that sitting above it, there's more. Up. And so this is, originally this was glued up to there. Right? Now, before we did the surgery, before we did this opening and closing, so this is now, so this from digging a trench really means remove an S1 cross, well, we're being sloppy about smoothness and corners and so on, so I'll just say S1 cross V2. Okay, it's really S1 cross a square, but that's fine. And so if we wanted to just glue it back in the same way, without changing the manifold at all, we just want to glue back in, that would be the same thing as gluing it back in so that this curve goes down, over, up, and then across the top. That's the original meridian, right? That's what bounded the disk before we removed this thing. Remember, meridian is the simple closed curve on the boundary of a torus that bounds a disk in the solid torus. Okay, but we're going to glue it so that, in fact, we're going to glue it so that we have we achieve a Dane twist across this. Well, so what does that mean? That means that this curve up here, we're going to put this back in. Maybe I should really draw it. I should really have drawn. Let me actually put let me draw one more picture. This. I want to draw the top of that, and so this is up here. This is again I cross sigma going up, I increasing, and so here's this the top of that trench that I have. And so up there, I see the meridian is there. So really, that's what the meridian used to look like, right? Now, when I glue with a Dane twist, I'm going to change that picture. I'm going to change that picture. What does the Dane twist do to an arc transverse? It makes it wrap all the way around. Remember, I had this picture. I purposely drew a Dane twist. The following way. I purposely drew a Dane twist kind of an annulus like this, sort of tilted sideways annulus. The Dane twist is, this is the Dane twist along C, where C is the center here, the main twist is such that a transverse arc like this goes to an arc that goes all the way around the back. Oh, I was very sloppy about it factors into positive or negative date twists. Okay, so I could go the other way as well. Actually, if it's closed surfaces, you can always use positive date twists. But that's not important. So what that means is that we're really re-gluing so that the image of this curve is not this, but is a curve that goes around. So we're going to change this to this picture. That's on top, but we're now going to glue so that this curve on the bottom, running here, on the side, is identified up here with, there's my annular neighborhood curve C, that's identified up here with a curve that goes to the right, around there, and then back. Okay, so what it really means is that we're filling in a disk. In a sense, we're making this curve glue to that. Another way to say it is, I could put all this back together. So I can do two things. I can split it open and then re-glue so that circle, that arc there, is mapped to the arc that goes all the way across there. Or I can split it open, remove this tunnel, glue it back together without the tunneling, and then put these transverse discs in. And if I put those transverse discs in, I put them in so the boundary goes like this, this, and all the way around there. Okay, so let's just look at the boundary of that. So there's our, so if we look at this sort of solid torus neighborhood, I'm now going to stop drawing all the sigma and just draw this. So what is this picture? This is supposed to be a solid torus. Okay, it's a solid torus in the sense that the right-hand end is glued to that left-hand side, right? And so the new meridian, so we glue the disk back in. We glue B2 cross S1 back in so that B2 cross the point bounds this curve. And the curve we're talking about is the curve that goes up. That. Okay, see where that came from? And so what is that, if I now draw that, or now draw a more standard picture of the solid torus. So this is our original solid torus with the original meridian. So this is the, let's say these two colors maybe. So this is original meridian. And then the way I've done it, it's twisting left, right? As I go around, this is a curve that goes around and moves to the left once. So the new meridian is going to be something like after surgery. Questions? If you buy that, then I claim that that is precisely a kind of surgery. So this is so another way to say that is i.e. what we could do is we we construct an embedding of B2 cross S1 as a neighborhood of this curve CI. So we really wanted to think of the curve CI as sort of running right through the middle of that solid torus. So the curve CI running right down there. I want to construct an embedding of this as a neighborhood such that the first thing is that the boundary of B2 across the point goes to the blue curve. And also I want a point cross S1, right? This point is in boundary 2. So I want to understand how the boundary of this solid torus is being identified with this T2 here, okay? And the point, I'm trying to specify this embedding of B2 cross S1, and so this goes to the green curve. Now you might say, so that is not the embedding of B2 cross S1 that is sort of obvious from this picture. In this picture, the obvious embedding of B2 cross S1 is, well, here's the B2's factor, and here's the S1 factor, right? And it just moves parallel. And in that case, sure, boundary of B2 cross point is going, well, this was supposed to be green, right? In fact, the original meridian, okay? Sure, boundary of B2 cross S1 was mapped to this, but then if I take a point on the boundary of B2, cross with S1, I'm pulling out a straight line all the way across, just, this sort of natural parameterization here. That's the zero framing that we were talking about. We're not using that zero framing. We're mapping it in by a twist, right? So as we go around, instead of keeping the B2s, the product with B2 happening like this, as we go around, we have to do a full twist, one full twist. And it's one full twist to the left as we go relative to this zero framing. Now, what if it had turned out that the new meridian was some radically different simple closed curve on here? For example, there are lots of simple closed curves on this torus. I could have had a curve that wraps 15 times this way while going 22 times that way, because 1, 15, and 22 are relatively prime. So, right, then I would get a simple closed curve. And in that case, because it would go around many times this way, I would not be able to extend this, I would not be able to find such an embedding of solid torus. The key thing is that if I'm going to embed a solid torus as a neighborhood of C, I have no choice of what the boundary of B2 cross point has to be. It has to be something that bounds a disk. And then the image of point cross S1 has to be something that intersects it transversely once. So I could draw any simple closed curve on the boundary here that's not homologically trivial and say, fill that in. And that would be a different kind of surgery called a rational surgery. And this is called an integer surgery because it intersects once. And these are the kinds, so once you do this, then you replace with S1 cross B2, where the S1 of this lines up with the boundary of that, and the boundary of this lines up with that S1. So in the usual way. And the point is now the green, so this goes there, and this goes there, and now the green curve becomes our new meridian. And that is precisely the kind of surgery that arises when you attach a handle along the curve CI with this particular framing. So notice that this, remember, a framing is a isotopy class of, you can think of it as two ways. You can think of isotopy class of trivializations of the normal bundle, or you can just think of it as an isotopy class of extensions of the map of the circle to a map of the solid torus. And so this, or anyway, this is a framing. This is a framing of CI, and the framing is actually, in this case, -1. -1 relative to the thing that we called 0. Because the thing we called 0 would have been, it comes from the surface, and if we draw a parallel push-off, it just goes in that direction. It's -1 because it twists 1 to the left. And so so we are doing -1 frame surgery, therefore n is obtained 3 by -1 frame surgery along this C1 union. The union of all these curves, just notice you displace them one on top of the other, right? So they're just, on a given surface, they may intersect lots, but I put them on parallel copies of the surface, stack them on the other. This is -1 frame, and just remember that's -1 relative to the framing. I should really say plus or -1, because if it was a Dane twist the other way, it would have been the other one, but relative to the framing coming from the signal. Okay, so those of you thinking about context structures and open book decompositions, if you take a 3-manifold with an open book decomposition and you want to change the monotone by a Dane twist, by a right-handed Dane twist, what you do is you draw a curve in the page, and you do -1 surgery on that curve, relatively, exactly the same thing. That's splitting, now you've got the pages going all the way around. If you're not are all of you in Cobordism? No. Okay, if you're not, that's fine, don't worry about it. If you are, you've got surfaces going all the way around and coming back, and then you've got a curve you want to change the monotone, you open it up, do a surgery, and do it back. It's exactly the same argument. I don't know, I think there may not be much more I can do to make that convincing to you other than suggest you look at your paper as well. It may have to sit with you. If you're not convinced, it may have to sit with you for a little while and absorb it. All right, so what does that tell you? Well, the point is now, these surgeries, this kind of surgery corresponds to adding a handle. Okay? So each such surgery, how to get X4? The 4-manifold open bounds. Well, so first of all, S3 is the boundary of B4, so the statement is true for S3, right? And then for each, so X is going to be equal to B4, the 0 handle union, 2 handles attached along C1 up to Cn in these frames. And we've already shown that that corresponds to precisely, and then each such handle attachment changes the boundary by exactly the surgery you want. Questions? Okay. So that's the end of the proof. Now, this depended upon knowing that the mapping class group of closed surface could be was generated by name twists along simple closed curves. I wanted to actually give you a Morse theory proof of that as well, although the original proof is sort of easier. But I couldn't quite figure it out. So there ought to be some sort of Morse theory proof which says, and this is related to my question I asked a while ago about an automorphism of the torus and trying to interpret that I said you take a particular Morse function on a twice function torus, and then you apply a certain automorphism of the torus, and you get a different Morse function. You want to see some sort of surf graphic in between, right? So, I mean, I think an interesting question is, so the question is sort of that I'm interested in is how do automorphisms of surfaces and generic homotopy for the Morse functions relate. I'll give you some idea of what I mean by this. This is, and the point is to get, so the goal is to get a Morse theoretic proof that name twists generate. With luck, I'll come up with that at some point, as you will. But the idea was to say, the idea here is that suppose, e.g., given some Morse function f from the surface to maybe it's a surface with boundary or not. Let's make surfaces with boundary at the moment. And then some phi from sigma to itself. Right, then you can get you can consider a generic homotopy f sub t from f0, which is just f, to f1, which is going to be f composing phi. Right. And suppose that you somehow are very lucky and f sub t has no births, deaths, or crossings, critical value crossings. So you look at your surf graphic and you just see the critical values for f sub 0, and then you just wander around and you get the critical values for f sub 1. Then I claim that actually means that, and that implies that up to isotopy, basically I'm just going to say that implies f0 is isotopic to f1. Where I mean, you can get one by pre or post, get f1 by pre and post composing f0 with isotopic and anisotopies. So they're basically the same. And so what that would say is that up to isotopy, f0 and f1 are the same, which means that, what does that mean about phi? That means that phi maps level sets. So up to isotopy, f0 equals f1. Isotopy f composed of phi equals f, i.e. phi maps level sets of f to level sets of f. Okay. And so that means that it does some, so now f might look like this. and then that's mapped by some phi, the same thing. And what it means is that phi respects level sets. And if it respects level sets, then notice that it also respects a decomposition of the surface into elementary pieces, like here's pants, for example. And then what you would want to know is that somehow you want to understand exactly, it would sort of do, for example, you know that you could actually make it the identity on, suppose you decompose your surfaces in pieces, right? You could make it the identity on various slices just by rotating, by isotopy, and on fixed level sets. And then you could decompose it into a bunch of slices on which is the identity. And then you'd have to understand the mapping class from, say, pairs of pants and cylinders, which is not hard to do. You can do that in terms of Dane twists. And then you'd want to say, well, what if there's a handle slide, for example? And the handle slide, or a handle slide actually, I've got a handle here and it slides, that actually is going to correspond to a Dane twist. I'm just sketching something out here. A handle slide should, of course, somehow sliding around the level set should be like a Dane twist along that level set. And then swapping levels, crossings, critical value crossings, should be just in order to get to the next Dane twist. You want to do a Dane twist, say, along this curve, and it's not a level set. So you switch critical point crossings until that's a level set, and then you do a Dane twisting. So somehow hidden in that, which I haven't quite nailed down, there's proof. That's a very sketchy idea for a proof that Dane twists generate a mapping class group. And maybe I'll find the right resource, the right reference, and figure it out myself. But anyway, so now I want to just say a few minutes about putting this question of this point that 3 manifolds bound 4 manifolds. Oh, I showed it down as a 4 manifold made with just 2 handles. That's why the 4 manifold is simply connected. Because to get a non-simply connected, anything non-simply connected, you need some non-trivial pi 1. Right? You can't get non-trivial pi 1, as you build up. If you attach a 2 handle in terms of homotopy, you're just attaching a 2 cell, and that's never going to create any homotopy trivial loops. So you need 1 handles to get non-trivial pi 1, and so if you only have 2 handles, it's simply connected. You could do, if you wanted non-simply connected 4 manifolds, you could do that as well, but you don't care. But forgetting about the simply connected issue, this fact that every 3 manifold becomes a 4 manifold, the larger context is the following. So I'm going to give a definition of oriented cobordism. The definition is that an oriented, I've been a little sloppy about cobordisms and not mentioned orientations, but an oriented endless one-dimensional cobordism is between oriented, and that's x between oriented n manifolds and 0 and 1 is also compact n plus 1 manifold x with the oriented boundary of x equal to minus m0 disjoint unit. Okay, so minus means m0 with the opposite orientation. So the reason for this convention is best exemplified by a cylinder, right? If you take if this is x and we have oriented circles, so if let's say how do we orient surfaces, let's say by outward normal and right counterclockwise rule, and then how do we, so that's our orientation of our surface, and then that orients the boundary according to my mantra I learned for orienting boundaries, outward normal first. So if I want to have a orientation on the boundary, I take an outward normal as the first vector and find whatever basis I need to complete that to an oriented basis. So that would mean since I'm doing this, that would mean this is the proper orientation of that boundary component. Okay? And then down here, okay, this is the orthonormal, so that's the orientation of that boundary component. Okay, and notice they have opposite orientations. But I want to think of this, I'd like to think of this as cobordism from the same thing, you know, from S1 going this way to S1 going itself. So this is really, this equals S1 going that way, and this equals minus S1 going this way. And the other reason you want to say it is if I have a cobordism from M0 to M1 and M1 to M2, you want to be able to glue them together in an orientation consistent way. And to do that, you should glue things by orientation reversing gluing maps along the boundary, because of the outward normal becomes inward normal. And so that's why, you know, I want the next one would be minus M1 to M2, and then you glue them together. The identity map would be orientation reversing. If that makes sense. And so now the next point to make is that oriented cobordism is an equivalence relation. Modulo set theoretic things, like not being able to take the set of all manifolds. And so, okay, so this gives the equivalence relation. And how do you check if it's equivalence relation? Well, the cylinder or manifold cross S cross interval shows that everything is equivalent to itself. The fact that you can glue cobordisms tells you that it's transitive, and then you can. The other thing is that minus X is a cobordism from M1 to M2. So you reverse the orientation of an X, you reverse the orientation of the boundary, this becomes bottom, that becomes top. So that shows that it's equivalence relation, right? And then the set, then the cobordism classes of oriented and manifolds acting as a group. And the group structure is, the group operation is, so the operation is, the operation is disjoint union. That's one way to state it. And it's actually or connected sum. When I say or connected sum, what I mean is, if you take the disjoint union of two manifolds, that's cobordant to the connected sum. What's the cobordism? Disjoint union of two manifolds cobordant to the connected sum. The cobordism is attaching a what handle? What kind of handle should be attached? A one handle, right? A one handle, because it just, a one handle glues a ball in one thing to a ball in the other. So the cobordism is attaching a single one handle. Okay, and if you check this well defined, whatever, it's not that hard. What about inverses? The inverse, so the inverse of the equivalence class of M is the equivalence class of minus M. Why is that? Oh, well, what's the identity? The identity is either empty set, right? Or at the sphere, or anything else that, the empty set or the sphere or anything else that bounds something, right? And then how do you see that this is the inverse? Well, to see that this is the inverse, you take the same cylinder again, but you think of this cobordism like this, right? So this is M and minus M, and this is a cylinder. And 1 cross M. You draw it this way, and it's a cobordism from M disjoint union minus M to the empty set. Okay. And so, well, there's this group. We've shown that, so that group is called omega. This group is called omega NSO. SO for oriented, right? Because there are various groups. You do all kinds of other cobordism relations you can consider, where you put various structure on the manifolds, and anyway, so this just means that it's oriented, and so what we've shown is, well, we've shown that omega 3 SO is just 0. Every 3 manifold bounds a 4 manifold, so all that talk about, because every 3 manifold is in the if you bound something, then you're in the equivalence class of the empty set. Because when you've got something with one boundary component only, it's Cobordism from the empty set to that thing, or that thing to the empty set. And it's not hard to see that omega 1 SO, every 1 manifold, closed 1 manifold bounds something, so that's 0. Omega 2 SO, every surface bounds something. This, of course, is non-trivial. It depends on the classification of surfaces, right? Once you know the classification of surfaces, then you do this. It's worth, what about omega 0?
Two elements.
So that depends on whether you want to do oriented points or not oriented points. Right. So if it's unoriented zero cobordism would be unoriented zero manifold. Oriented zero manifolds are points. Oriented are points with pluses or minuses. Actually, this is actually Z. You can't. Again, that's just some. It's Z2 if you want. If you don't care about orientations, but it's Z because if you sort of have a bunch of points with pluses and minuses, then you can't, use a convention on one manifold oriented, and you can't change the sum of the pluses and minuses. Well, okay, the thing we're going to use next is that omega 4 SO is Z. And the generator for this, so the generator for this is a single point. The generator for this is going to be generated by the equivalence class of CP2. And whether or not I just pull that out of my hat or give you a proof depends upon what happens on Friday. I'll either use this with unproved or I'll try to give you a proof. In particular, CP2 does not bound.